First of all, I guess I'd also like to thank the organisers for giving me the chance to speak in front of such a large and illustrious audience. I'll just quickly introduce myself. My name is Glyn. I'm a second year part-time PhD student at Heriot-Watt, working with James Cruz. I'm one of the expanding mob of mathematicians at Heriot-Watt who are interested in energy systems. My talk is going to be yet another talk about using storage to control uncertainty in power systems. So I apologise, there will be quite a lot of repetition with some of the other ideas we've already seen. So sorry about that. Okay, so this is the structure of what's going to happen. First of all, just give a bit of background and try and motivate the sort of model I'm looking at. James has already done that for us, so hopefully we're all salivating at the prospect of this talk. I'll then describe the components of the model and then solve the very simplest case, and then try to extend some of the ideas from the simplest case to more complicated cases. In the spirit of the subject of this talk, the time for questions at the end will act a bit like a storage buffer. So if I end up spending too much energy on the previous parts, reduce the time for questions to try and meet the demand for a 30-minute talk and lunch. Okay, at this point I'll try and maybe just make a disclaimer. James has already done this quite well. These are simple models. They are not going to capture everything about the situation. I'm sure lots of people in the audience will be able to pick holes in them in some ways or other. But the point was to try and gain some kind of insight into the sort of what's going on in these sort of structures. So it's a bit like learning to crawl before learning to run, or in this context, a bit like trying to operate one of these handheld windmills instead of operating this big complicated network. So this picture up in the top right, that's me when I finish my PhD. But at the moment I'm this baby with this toy. Okay, motivation. So lots of questions about storage floating around. Put some of them up here. So can we use a storage facility to control the uncertainty you get in the electricity network when you have more and more wind power coming on? What sort of storage am I even talking about here? Am I talking about your pumped hydro, your batteries, or some virtual storage from demand management techniques? How much storage do we need? Once we have a level of storage, what's the best way of operating the system to control it, to minimize cost in some way? How do you actually quantify the benefits of what you're doing? Are there better uses for the storage? So if we have the storage, are we better off using it for something else rather than this purpose? So there are lots of questions floating around, which I'm not going to try and answer really. But if you were, you might have a very rough approach. Might be so you decide what storage you're talking about, what sort of mix. Once you've got a certain level of storage, figure out how do you optimally operate the system with that storage. Try and perform some kind of cost-benefit analysis, which has to take into consideration your opportunity cost for not using it for something else. Try and repeat that for different levels of the storage or different types of mixes, and finally come up with some kind of optimal plan for storage and controlling uncertainty with it, and then go and build it like these guys are doing. Anyway, my little model is looking at this particular section of the overall chain. So just how do you actually go about controlling the uncertainty? What are you doing in this system? Okay. I'll also apologise that the notation I'm using is totally different to the notation which James said I was going to be using. Not quite as coordinated as it could have been, but okay. So the model. So again, I've got two supply types, renewable supply and a conventional supply coming into the grid, which simplifying down to just a single point, trying to meet the demand, and we've got this storage facility there. So when you end up over-generating, you fill up your store. When you under-generate, so when the wind doesn't blow quite as much as it was, you will under-generate and you will empty out your store to balance it out. So your store will be subject to a maximum capacity of B and minimum level of 0. So that all sounds very simple. What's the problem? So as has been mentioned so many times, everybody knows the conventional supply has to be powered up in advance because of the long lead times and the ramp constraints and what have you. You might also have problems because your storage is inefficient, so every time you try and put some energy in, you'll lose some energy. As James mentioned, it's just discretize the whole thing. So we're doing single time steps, and we're thinking of energy bundles transferring from coming in and then transferring it at the end at the time step to top up the storage or empty the storage. Okay. So within this framework, the issues of variability and predictability are kind of both intertwined, so it's useful to kind of transform the model a little bit to try and separate out what's going on. So if we think of big T as the time which we have to set our conventional supply, we can separate out what's going on into what we're predicting is going to happen based on these T time steps in advance, and the errors you get as a result of that. So the variability problem is to do the top box, third box, and the third box, and the top box on the right. So the three predicted components, and the uncertainty problem is to try and come up with a good strategy to put in a bit of extra conventional supply to deal with all these errors which are coming in. I put in errors for the demand and the actual delivered conventional supply as well, but really what I'm thinking about is the errors in the predicted renewable supply. Okay, so that makes it look a little bit more complicated. You just group together all the errors and you net off the predicted components from the set conventional supply. Simplifies down to this picture. So what we're trying to do is set the control big T time steps in advance to try and in some clever way deal with these errors which are coming on. And we've got this storage facility to use. Okay. Right, so how do we actually do that in a clever way? What are we actually trying to achieve here? There are choices how you might want to set up the problem. So here are a few of them. So do you want to try and minimize the expected energy they actually spill from the system? So when you filled up your storage and you try and fill some more, that energy will just get spilled. And so there's a spillage cost. Or are you trying to, in some way, minimize the total amount of conventional generation that you're using? That is what we're trying to use renewables. One of the reasons we're trying to use renewables here. So are those two things in fact the same? In some cases. Yeah. And what you might try and insist upon is that probability of not meeting your demand is sufficiently low. So what I mean by not meeting demand here, so when your store empties and goes below zero, well, it would go below zero, it gets restricted at zero, that means you've got a demand not met in this setup. So in that case you would probably have to resort to expensive measures which you don't really want to go into, such as the expensive fast ramping generation or importing energy, something like that. So that's a situation you might want to avoid, and so you might try and insist that you avoid that with a certain probability. Or if you want to do something more sophisticated, you might actually try and model the costs from what happens if you don't meet it. But I'm a simple man, so I've picked option A and option C. Okay, so the error process, what's happening here? So the error process is clearly a key assumption here, and it's going to drive what the best strategy is. So your wind prediction is going to have some ultimate solution being developed, which is some mixture of these periodic meteorological forecasts combined maybe with some clever mathematical time series. You can maybe correct these based on the real-time power outputs that you're seeing coming through. So there's some ultimate solution coming out here. I don't really know too much what it's going to look like at the end, and what your errors will actually look like. So at the moment, the model just puts simple assumptions in. But in general, one point I would like to make is that when you're setting your control strategy now, it's maybe not quite enough to think, have your sort of expanding funnel of doubt picture about your errors. You also need to think about what your forecast will look like in the future when you make future control decisions, because your current control decision will impact future control decisions as well. So we've had a couple of these statements earlier in the week. My attempt was what's important is not what you know now, but what you know you'll know. So it's like forecasting your forecast almost is going to be important here. But maybe to start off with, we could just assume the error process is stationary. So particularly that will mean that your one time step ahead errors are all IID, your 2 time step ahead errors are all ID, etc. Okay, so let's just summarize the model setup here. This sounds a bit like a dynamic programming problem, so let's put it in dynamic programming speak. So we've got the state variable of the current level of storage, which is where you are now. You've got these errors coming in. So maybe not a particularly rigorous notation for what your error process is like, but if you're in the stationary case, you might say that if you're at time tau and trying to predict at time t, so your t minus tau ahead errors might have this particular density and distribution function. Our control variable, that's how much extra conventional we're going to set to deal with that, with the errors. So that could be positive or negative, but that's denoted by u, t. And we've got a control system which is saying we're going to set this control every single time period, and the control is going to apply big T time periods in advance. So we've got the plant equation, which describes how the system evolves. So that is saying your storage level at time t is equal to your storage level the previous time step plus the amount that gets added in. So that's your amount of your error plus the extra amount of your control, but subject to the fact that if you're adding in, topping up your storage, you're going to lose some, so that an efficiency factor will come in, and then it's bounded above by b and flowed by 0. And for the mathematical buffs in the audience, which is quite a lot of you, as James mentioned, that this is an example of a Skorohod double reflection process. So, okay, what's the cost? The cost is the energy loss. The cost at time t is the energy that you lose at time t, and that's given by the efficiency losses which is your 1 minus k times the amount that you try to top up the store, plus your overspill losses. So that's if the store gets filled up, and then anything above will get lost for spillage. Okay, so there's the model. Let's try and solve it. So strip it all back, look at the very simplest case we can think of, because we stand a chance. If you just do one time step ahead and you have an efficient store, then the problem can be restated as simply at time 0 you're trying to minimize the expected average cost over a particular time horizon, subject to your probability of your storage emptying at any time being less than epsilon, which is your limit that you've decided is sensible. Okay, so here's a result and a proof. So it turns out the optimal strategy, if you just have a time horizon of 1, is to set your control as minus S0 minus this quantile function. So proof of that is pretty simple. You just look at what's your constraint telling you. Your constraint's telling you that you have to limit your probability that your storage is 0 to a certain level. The probability that your storage is 0 is just the probability that your error less your control, or your error plus your control is less than a certain value, which is actually your current value of the storage, and so that just equates to the expression there. So you observe that to meet the constraint, your control has to be greater than this value here, and then you just observe that your costs are increasing in your control. So you want to take the control as low as you possibly can to meet that constraint. So just set it equal. Okay, so there's a result and a proof. Starting to feel a bit happier now. We could now know what to do if we've got a time horizon of 1. Next question is 1. So if you run the system for longer than 1 time step, is it the same answer? Okay. First of all, let's do a picture. Explain what's going on here. So you've got your storage level, current storage level S0. You're wondering whether to increase or decrease your control. You know that your error, you're going to have an error with a particular distribution, so without the control you might end up according to that picture there. And so essentially what you're doing is, with your control, is you're shifting that picture up or down. And then your constraint is telling you that if you shift it too far down, there's going to be too big a probability that you don't meet your demand. But clearly you want to shift it down, because otherwise you've got some extra expected costs from your spillage. So there's this optimum level to try and shift it down to try and minimize your expected costs subject to your constraint. So that's what's going on. So a quick note that your solution is linear in your current storage level, and it doesn't depend at all on how big your storage is, and also the target point that you're aiming for doesn't depend at all on how big your storage is or your current storage level. So that all sounds like it's working quite simply. Okay, so if we try and run for more than 1 time step, luckily we can show that it's exactly the same strategy that you use to set your first control. So here's a proof by words. I'll skip that and go to the alternative form of proof, which is the proof by picture. Okay, so the idea is basically we test out the previous strategy. We think that's going to be the best one. So in our first strategy, we could do that, or we could do something else. So our previous strategy was this U1 star. Our alternative strategy is going to be U1 prime. So if we use U1 star, we aim down for this level. We know we can't aim down further because we'll break the constraint. But what else could we do? We could come down less. If we come down less, well, what's going to happen? We're going to have a lower expected cost over the we're going to have a higher expected cost over the first time step, but maybe that might cancel out with future time steps or something. Okay, does it? Well, no, because you can just simply notice that in the next time period, no matter where you ended up, you could just simply alter your next strategy to set all future costs being the same. So this is a feature which is pretty handy. It means the solution does not depend at all on what's happening later on, compared to just when you're actually setting the strategy for it. Okay. And this is not the case when you try and introduce ramp constraints or the efficiency of storage. Simple case, it works. Okay, so once you know the optimal strategy, you can come out with a number of other results by just substituting in what that optimal strategy is. I'll skip over that one as well. And we'll have a recap of where we've got to. So, in the spirit of making predictions, this is what I thought would probably happen. Probably have to reduce part 3. Not too far off, a couple of minutes. Okay. So how do you extend the simplest case? Okay, so say we, instead of just doing one time step ahead, we wanted to do 2 time steps ahead or more, lots of time steps ahead. Well, we can use this similar ideas, similar principle for how to get the answer. So what's happening? We're starting off at our initial storage level. We've got an error coming in that we know from the forecast. We've got a previously set control value that was set sometime in the past, so we know what that's going to be. So in some way we can know what the distribution of the storage is going to be like at the first time step. Might have some masses of probability at the top or at the bottom, both. Anyway, we know what's happening. If we know the evolution of what the process is going to be, we then will know what the second error, where that will take you, and so you have a knowledge of where you're going to end up at the point that you're trying to set the control for. So again, you use the same idea. You want to limit the probability of failing at that time step, so you set the control to try and get you to a particular target level, which does that based on your distribution of, well, your joint distribution really is of the errors which are happening between now and that time of control. Okay, and same idea, lower control means less expected overspill. Right, so now, how does that change the nature of the solution? Well, for a start, because it's complicated, because you've got a few things going on, it's no longer linear in your S0. We have a solution which will depend on your B, which is your capacity, because you might get stuck, and so at the top or at the bottom, in between, so that depends on how much room you've got to play with. But it's still the case that our target level that we're trying to target doesn't depend on where you start. It doesn't depend on the total capacity, because all you're trying to do is make sure that you're far enough away that you don't hit 0 or go below 0. And again, we've got the lucky feature that the solution doesn't really depend on any errors after the time we're trying to set. So these forecasts of forecasts later on don't really come into play yet. Okay, so that's extension 1. So to try and convince you that the solution really isn't linear, I've calculated it in a simple case where we've got simple IID normal errors, and so here are the results for the two time step case with different values of the sort of intermediate control that would have been previously set, and see, it's not linear. Okay, so the question we might want to ask is, how much better is doing it 1 step in advance compared to doing it 2 steps in advance? So to do that, I've written a little model that can run these simulations rather than trying to figure it out, and got the results here. It can make quite a difference depending on the size of your storage facility. So the black line on the left, that's if we do it 1 step in advance. Blue line is if we do it 2 steps in advance. And I've plotted the lost energy against the buffer capacity. So run the same set of errors under all these systems and with different buffers to see what would happen. I've also put in the green line, which is what happens if you don't do anything at all. How much energy do you lose? That's looking a bit odd because it's so low, but of course if you don't do anything at all, you don't manage to meet your constraints. So in reality, if you wanted to meet your constraints over the long run or something, that line would shift up above the other ones. Okay, so that was extension 1. There are 3. I might just have time to quickly do number 2. So this is when you introduce your inefficiencies of your storage. So I've got this factor k, so it might be 80% or something. So you lose 20% every time you try and top up your storage. So as mentioned before, your cost function looks like that. Now that it gets a bit more complicated, because you might lose energy when you overspill, but you also lose energy when you try to top up. So maybe it's good to go down again, because that will decrease the energy you expect to lose from overspill, and it will also decrease the energy you expect to lose from top up. But well, there's a balance here, because if you go down too far now, you won't have room to go down again next time. So this is some kind of balance that you need to strike, and that's why your future control actions do come into play. So it's much harder, and the nature of the solution will change quite a lot. So to illustrate that, I've got this synthetic example that I made up to try and demonstrate the key features here. So here we've got one step ahead errors that all look the same, and they can either take a really big value of 20 with very low probability, 10 with very low probability, or you've got these kind of medium values. It can either go up or down by 2, 9% of the time, or by 1 with 40% of the time for each of those. So this is an example which has been specially constructed to try and highlight my point here. So you've got three strategies here which you might try and use. Number 1, you might try and use the same target point strategy as before. Number 2, you might try and do nothing at all, just let the system run. And number 3, well, here's an idea. What happens if you try and just decrease by 1 every time? If you're decreasing by 1 every time, you're going to save that increased cost for when you we're trying to increase by 1. And you could do that twice and save that twice. Right? So there's another idea. So I was going to end with a quiz, see if anyone could predict the order of which these 3 strategies perform. And Jean-Yves isn't here, I'm sure he could. Or do they all, in fact, have the same order? And so any votes for target point strategy A, which was the initial strategy? You're allowed to abstain. Well, everyone will probably abstain. Okay, no votes. Any votes for the do nothing strategy? No votes. Any votes for the decreased by 1 strategy? No votes. Any votes for they're all going to be the same? No votes. Okay. Well, the decreased by 1 strategy in this case works, is the best one out of those 3. So that just shows you that it's not the same effect as where you're just targeting a particular case. So, right, summary. Got a simple model here to try and explore how you can use storage, how you should try and to manage the uncertainty in the power systems. In the very simple cases, there's a simple analytical solution for how best to do it. And then we've tried to extend and explore the nature of the problem when you introduce further time lags, the storage inefficiencies, and the ramp constraints was the final side as well. So thanks very much for bearing with me. Happy to try and take any questions.
Okay, so maybe time for one quick question.
Well, there is a lot of literature on reservoir management using stochastic programming. So why don't you refer to that literature? And also, why do you specify you set up your model using probabilistic constraints, which in general introduce complications? So, well, my question is, why don't you refer to the hydro management literature?
Good question. I probably, I'm not 100% sure exactly which bit of this has been done.
The problems
before,
are quite similar.
So there probably is quite a lot of overlap with.
And it has been solved for very large systems like in Brazil.
It's a fair point. This is the problem that I've been working on. I've been set to work on. So it's a good point. If you could direct me to, if you happen to know of particular papers which deal with this, I'd be very interested to see them. Thank you.
Okay, so let's thank the speaker again.